In this video, we're going to do a little side exploration of a topic that you may not have thought of because it went by fairly quickly. When we defined the definite integral, say this integral from 1 to 3, 2 to the x dx, that would represent the area under the graph of 2 to the x between x equals 1 and x equals 3. This is now our notation for that area. When we introduced the definite integral definition, we said it would be the left-hand estimate of that as n went to infinity. But you might think, well, couldn't we use the right instead? And the answer is, of course, yes. The whole point that we're going to go through in this video is to recognize that when we use smaller and smaller intervals, it doesn't matter which estimate we use. So we pick one and trust that when the number of intervals gets small, it won't matter which one we use. One way to look at this is to look at our graph again, 2 to the x here, and we're going to divide the interval from 1 to 3 into two subintervals. So nice delta x being 1, from here to here is 1, from here to here is 1, that's our widths. And when we calculate the left sum with two intervals for that, we're going to go up to the graph at the first point, that'll be 2 to the 1, and then we'll go up to the graph at the second point, that's 2 to the 2, and we're going to multiply by the width in each case. So again, these are rectangles, height times width plus height times width, and that's going to give us 4 plus 2 is 6. If we draw it, it would be this sum here. We can contrast that with the right-hand estimate with two intervals. The right-hand estimate on the first interval, we're going to go to the 2 and build our rectangle, and it's going to be 2 to the 2 high, but still 1 wide. That's the width down here. And on the second interval, we're going to be at x equals 3, but we want to find the height. That's 2 to the 3, and again a width of 1. So height times width again. 4 and 8 is 12. What we want to focus on here is how different are they? Well, the difference is going to be 12 minus 4. It's 12 minus 6 rather. And that'll be 6 difference. So the area that's included in green but not in red is 6 total. That's a pretty big difference. It's a pretty wide range between those two estimates. But what if we repeat that calculation with 4 intervals? So again, we won't go through the full sketch here, but we'll note that if we're integrating between x equals 1 and x equals 3, and we divide that into 4 intervals, delta x now will be 3 minus 1, this whole interval width, cut up into 4 pieces, and that would be 2 over 4, or 1/2, which makes sense. If I do a half and a half and a half and a half, I'll get from 1 to 3. Going through the calculations, the left estimate with 4 intervals, we're going to start at 1, so I'll have 2 to the 1 times delta x times the width, and that width is 0.5. Then we're going to be at 1.5, and we're going to go up to the graph. So that'll be 2, here's the function we're using, 2 to the 1.5 times the width. And we should have 4 terms in total. You can start to see the pattern early on. The next point is going to be 2, we go to the graph, and the last point is at 2.5. So we'll have 2 to the 2.5. And we can factor out the 0.5. I'll add up all the other values with the calculator. These fractional exponents are a little more challenging. Can't really do those in your head. We end up with a value of around 14.485. And dividing that by 2 or multiplying by 0.5, we get 7.243. So the left estimate that we could sketch out if we wanted to, going all the way to the middle there, is a little low, but it's 7.23. Computing the same thing with the right-hand estimate, we should see something a little bigger, because using the right-hand endpoints will give us an overestimate. It'll have all the same pieces. I'll write it out explicitly here to get the practice. On the first interval, we're going to use the right-hand endpoint, so that's the 1.5 times the width plus, you can see the pattern again here, we're going to use 2.5 on this interval, and we will use 3. Let's finish that term first. On this last interval, we would use 2 to the 3 as our height. Doing a different color here. That would be the last rectangle with right, and 0.5. That would be our whole thing. Adding all that up and doing the calculations, we end up with 10.243. Well, the difference now is going to be, actually we can just see it there, it's 3. So by using more intervals, we narrowed the difference between those two estimates. Going back a slide, we had a 6 before, now we've reduced the difference to 3. In other words, the left and right estimates are getting closer to each other. And when we go to calculate the exact area, we're going to want to use an infinite number or more and more rectangles and find the limit. Now we generalize to an unspecified but presumably larger number of intervals, and we're going to let this number get bigger and bigger. The left sum with n intervals is going to have a nice structure. Let's do a quick little sketch here on the side, noting that we're moving from 1 to 3, but that we also have another notation we can fall back on, which is this x subscript notation. And we also notice that delta x would be, again, the width of the entire interval, 3 minus 1, divided by n. So we'd have a width involved here. If we're doing the left-hand rule, we would always use 2 to the 1 as the first height, and then we multiply by delta x. Then the next point we would use is x1, and then we'd have delta x. And then we'd have 2 to the x2 and delta x. I'm just going to move this up out of the way for a moment. We'd have a bunch more terms, and then the last term we would use would be 2 to the x sub n minus 1 times delta x. On this last interval, we would use this point to get our height. How does that compare to the right-hand sum? Well, for the right-hand sum, we don't use the 1 value. We start off at 2 to the x1. I'm going to put it aligned here. You'll see why in a second. On the second interval, we would use the x2, so that'll show up as well. We'd have a sum. On this last interval, we would say, or the second last interval, we would use xn minus 1. We'd say, let's go to that x coordinate, then go up to the graph. That'll be our height. Then we're going to multiply by width to get a rectangle out of that. And then we would also use 2 to the 3 on the last interval for the right-hand sum. That's not particularly helpful, but if we're interested in the difference between them, writing it out like this is tremendously helpful because we can do, let's do the right minus the left. With an n in there. If we take all of these and subtract all of these, imagine putting a big negative sign in front of all this, this minus this is going to cancel, this minus this, they're perfectly matched all the way along, except for the 2 to the 3 times delta x, and then we would subtract the one remaining term, the 2 to the 1 times delta x, or delta x times 8 minus 2, or delta x times 6. If you go back to the earlier slides, we could actually have shown that this applies to the earlier calculations we did longhand. Here we've been able to shortcut the process by noticing the common features in the left and right sums and the only two terms that are different between them. Well, why is this important? This is important because we can then ask the question, what happens as we use more and more intervals? If we have left of n minus right of n, so we just flip it around here, that would be negative delta x times 6. As n goes to infinity, remember that delta x is 3 minus 1 over n. If n is getting bigger and bigger and bigger, the size of each interval, delta x, is going to 0. It's important to be able to translate these symbols, n as the number of intervals and delta x as the width of each interval, in your mind immediately. It makes these written out calculations more meaningful as you go through it. If delta x is going to 0, then that implies that the difference between the left and right sums, well, all it is a delta x times 6, they are going to 0 as well. And so that is telling us the left-hand rule, or the left-hand sum, is going to be essentially the same. Let's write equals here. Is going to equal the right-hand sum for n going to infinity. What does this tell us about what would happen if we defined our exact area calculation, the definite integral, with the right-hand rule or right-hand sum instead of the left? We get the same answer. The key is the number of intervals used. As long as the number of intervals is going to infinity, then it doesn't matter what you do on each subinterval, how you calculate heights. They're going to get closer and closer together no matter what you do. We're focusing on the fact that we're using smaller and smaller and smaller intervals on our overall length that we're integrating over. All right, now that little digression was much more about the technical side. We're now going to focus as we go forward on this integral symbol, what it means, tying it back to the areas again, and not concerning ourselves so much about the left versus right, which one's better or worse. In this case, in the limit, they're equal. We're also going to spend some time looking at where would this integral come from. We've seen velocity and distance calculations, but there might be other scenarios that give rise to integrals fairly naturally, and then we might still estimate them using a left or a right sum to get a ballpark. Those won't be exact unless we have that infinite number of intervals, but we can at least do rough calculations using these estimating tools as a springboard to getting close to the exact areas we might be more interested in.